For decades, the M1 Abrams was called the world's invincible tank. But why are so many uncomfortable questions being asked today? Was it truly the greatest tank ever built? Or did its legend grow larger than reality? In this video, we'll uncover the engineering secrets, the hidden weaknesses, and the battlefield moments that shaped its reputation. And at the end, you'll discover whether the M1 Abrams really earned its legendary status. If you're interested in tanks, secret military projects, and forgotten war machines, be sure to subscribe to the channel and turn on notifications. There are many more fascinating stories ahead. Enjoy the video, and let's continue. Imagine a tank that for decades has been considered a symbol of absolute superiority. A machine whose appearance on the battlefield forced enemies to change their plans and allies to feel confident. Its name has long since transcended military reference books. Films are made about it, books are written, debates rage on forums, and it is still called one of the most formidable main battle tanks in the world. This is the M1 Abrams. But are we really looking at a nearly invulnerable machine? Or has a significant part of its fame grown out of resounding victories, a carefully constructed reputation, and fortunate circumstances? That is exactly what we will find out today. Over the decades, many myths have grown up around the Abrams. Some claim that it is practically impossible to destroy. Others are certain that modern anti-tank weapons have long since stripped it of its former advantage. The truth, as usual, lies somewhere in between. To understand this issue, it is not enough to watch a few clips from the battlefield or compare figures in a table. We need to understand how this tank became a legend in the first place, what engineering solutions made it so famous, and why, even decades after its appearance, it remains a benchmark against which new combat vehicles continue to be compared. From the very beginning, American designers did not create the Abrams as just another tank. Their task was to combine high firepower, reliable protection, and exceptional mobility in a single vehicle. It was precisely the combination of these three qualities that would later become the main reason for its fame. Already, the first production vehicles had a four-man crew consisting of a commander, gunner, driver mechanic, and loader. The American military consciously retained manual loading, refusing to adopt an autoloader. This decision allowed an experienced loader to maintain a rate of fire of up to 8 and sometimes even 10 rounds per minute, while also providing greater flexibility in choosing the type of ammunition depending on the situation. The power pack was no less unusual. Instead of the customary diesel engine, engineers installed a gas turbine engine, the AGT 1500, with 1,500 horsepower. This solution dramatically improved the vehicle's dynamics. Despite a weight exceeding 60 tons, the Abrams can accelerate on highways to nearly 70 kilometers per hour. The gas turbine provides smooth acceleration, low vibration levels, and rapid speed buildup, allowing the tank to swiftly change position even on rough terrain. True, these advantages come at the cost of high fuel consumption, but we will discuss that in detail later. Another reason for its legendary reputation was the unusual armor design. When creating the Abrams, the Americans used multi-layer composite armor developed on the basis of British Chobham technology. Instead of a single massive steel plate, the frontal projections of the hull and turret received a complex package of several materials, capable of much more effectively resisting both kinetic armor-piercing projectiles and shaped charge munitions. It was this design that became one of the biggest technological breakthroughs of its time and made the Abrams frontal armor a subject of intense study worldwide. The main armament was no less impressive. Later versions of the tank received the smoothbore M256 cannon of 120mm caliber, built under license from the German company Rheinmetall. The high muzzle velocity of modern armor-piercing, fin-stabilized, discarding sabot rounds, precise two-plane weapon stabilization, and a fire control system that was advanced by the standards of its time allowed targets to be engaged at long ranges even while on the move. For the crew, this meant the ability to deliver aimed fire in situations where many previous generation vehicles were forced to stop. Special attention was also paid to crew survivability. The ammunition stowage was placed in the turret bustle, separated from the fighting compartment by sturdy armored bulkheads. Blowout panels were located above the ammunition. If the ammunition ignited, the energy of the explosion was directed outward through the turret roof rather than into the vehicle. This solution significantly increased the crew's chances of leaving the tank even after extremely severe damage. This feature would later become one of the most discussed design characteristics of the Abrams. But a reputation is not born only from specifications on paper. History knows many vehicles with outstanding numbers that quickly disappeared after their first serious trial. The Abrams found itself in a different situation. Its real legend began to take shape when engineering solutions first encountered real combat conditions. It was there that it became clear which technologies actually worked and which beautiful manufacturer promises did not pass the test nearly as confidently. And this is where the most interesting part of the story begins, for a tank that for some became a symbol of American military power, and for others, an example of just how much a loud reputation can differ from reality. Every legend begins not with triumph, but with a problem that can no longer be ignored. The history of the M1 Abrams was no exception. By the early 1970s, American military leaders were increasingly coming to the conclusion that existing tanks no longer corresponded to the threats that were rapidly changing the face of a potential war in Europe. On the other side of the continent, the Soviet Union was serially producing new vehicles, improving armor, armament, and tactics for the use of armored units. If not long ago, superiority could be ensured by the quantity of equipment, now the quality of each individual tank was becoming decisive. The main tank of the US Army at that time remained the M60. Despite numerous upgrades, its capabilities were gradually approaching their limit. The cast turret no longer allowed for a significant increase in protection without a sharp increase in weight. Homogeneous steel armor handled the threats of its generation well, but the development of armor-piercing, fin-stabilized, discarding sabot and shaped charge munitions was rapidly reducing its effectiveness. American analysts understood that the next conflict might not resemble previous ones at all. Particular concern was caused by the new Soviet tanks. They had a low silhouette, more advanced armor protection, and powerful smoothbore guns. This meant that the future American tank had to not just catch up with a potential adversary, but gain a significant technological margin for many years to come. The military formulated highly ambitious requirements. The new vehicle had to confidently engage targets at long ranges, detect the enemy first, take advantageous positions faster, and withstand hits from the most dangerous munitions of its time. At the same time, it became clear that achieving such a result by conventional methods was no longer possible. Simply increasing armor thickness quickly turned the tank into an excessively heavy vehicle. Every additional centimeter of steel plates meant an increase in weight of hundreds of kilograms, increased load on the suspension, reduced mobility, and more difficult transportation. Designers faced a difficult choice: preserve mobility or maximize protection. It was then that the idea arose to seek new materials and a completely different approach to armoring. Equally serious requirements were placed on the target detection system. The experience of numerous exercises showed that in modern combat, victory goes not to the one with the thickest armor, but to the one who sees the enemy first and opens accurate fire faster. Therefore, the future tank was initially designed with the integration of modern sighting systems, a laser rangefinder, and a digital ballistic computer in mind. These systems were supposed to automatically account for the range to the target, propellant temperature, gun tube wear, crosswind speed, vehicle roll angle, and many other parameters, significantly reducing the time between target detection and the first shot. Mobility was not forgotten either. The military demanded that the new tank maintain high speed not only on highways but also over rough terrain. For this, designers had to recalculate the suspension characteristics. It was decided to use an independent torsion bar suspension with hydraulic shock absorbers on the most heavily loaded road wheels. This scheme provided smoother movement over uneven surfaces, increased vehicle stability when firing on the move, and reduced crew fatigue during long marches. Special attention was given to the transmission. The future tank had to confidently climb steep slopes, quickly change direction, and maintain high maneuverability even at significant weight. This is why engineers began developing a new, automatic hydromechanical transmission with several forward and reverse gears, designed to transmit significantly more power than the previous generation of American tanks. Another mandatory task was protecting the crew from weapons of mass destruction. Designers provided for the sealing of the fighting compartment, a collective protection system with a filter ventilation unit, and the creation of a slight overpressure inside the tank. Thanks to this, contaminated air could not freely enter the vehicle even when individual hatches were briefly opened. For the military of the Cold War era, such requirements were not a luxury but a necessity. However, the more thoroughly specialists worked out the technical requirements, the more obvious it became that creating such a vehicle quickly would not be possible. Each new requirement entailed dozens of engineering problems. More powerful armament required strengthening the turret. Strengthened protection increased weight. Increased weight demanded a new engine, a more robust transmission, and a redesigned running gear. At some point, it became clear that the US Army needed not just another modification of an existing tank, but a completely new combat vehicle, created practically from scratch. But before the world saw the first Abrams, designers had to go through one of the most complex and controversial stages in the history of American tank building. It seemed that the requirements had already been defined, and all that remained was to assemble all the best ideas into one machine. But it was at this stage that it turned out that creating a new generation tank was much harder than even the most experienced engineers had assumed. The project constantly faced technical difficulties, political disputes, and rapidly escalating costs. At one point, there was a real danger that the Army would be left without a new main battle tank altogether. The history of the future Abrams did not begin with itself. The first attempt was the joint American-German project MBT-70. It was supposed to combine the best engineering solutions of the two countries and become the most advanced tank of its time. However, it quickly became clear that the Allies had different visions of an ideal combat vehicle. German specialists insisted on some technical solutions, while Americans insisted on completely different ones. Disagreements touched on almost everything: turret design, armament, power plant, production costs, and even crew ergonomics. Armament proved to be particularly contentious. The American side favored an unusual 152mm gun launcher capable of firing both conventional shells and guided anti-tank missiles. On paper, this looked impressive, but in practice, the system turned out to be too complex. Ammunition was bulky, rate of fire decreased, and missile reliability left much to be desired. German engineers proposed keeping a classic tank gun, considering it a more practical solution. Time showed that this approach was the correct one. The vehicle layout raised no fewer questions. One of the most unusual features of the MBT-70 was the placement of the driver inside the rotating turret. Regardless of the gun's position, his seat automatically maintained a horizontal orientation. The solution looked extremely modern, but it significantly complicated the design, increased turret weight, and created additional risks if the rotation mechanism was damaged. Ultimately, such a scheme was abandoned. When the joint project finally reached a dead end, the Americans had to start virtually from scratch. This is how the experimental M1 tank emerged. Despite its external resemblance to the future Abrams, it was actually a huge experimental platform on which dozens of different engineering solutions were tested. Designers tested armor variants, internal component layouts, new fire control systems, and various types of power plants. In the final stage of the competition, two main contenders met. One project was presented by Chrysler Defense, the other by General Motors. The main difference was hidden not outside, but inside. Chrysler bet on a gas turbine engine, while General Motors continued to develop a powerful diesel variant. Trials lasted many months and took place in a wide range of climatic conditions. The vehicles covered multi-kilometer routes over sand, mud, rocky terrain, and cross-country to determine not only their maximum performance, but also their reliability during long-term operation. During testing, engineers meticulously analyzed every component. The torsion bar suspension's performance at high speed over rough terrain was checked. Loads on road wheels and idlers were measured, and the durability of tracks with rubber metal joints was assessed. The turret's stability during intense firing and the effect of recoil on the accuracy of subsequent shots was studied separately. Even minor changes in weight distribution could affect the entire vehicle's handling. Great attention was also paid to internal layout. Designers aimed to minimize maintenance time as much as possible. The power pack was designed on a modular principle. This meant that the engine, along with the transmission, could be removed from the hull as a single unit and replaced in the field significantly faster than on previous American tanks. For an army expecting to conduct prolonged combat operations far from repair depots, this solution was of immense importance. In parallel, the electronics were being improved. Even then, developers understood that modern instruments would occupy a significant portion of the vehicle's internal volume. Therefore, cable harnesses, control units, and diagnostic equipment were placed so that they could be quickly accessed for repairs. In addition, for the first time, great attention was paid to an onboard system for monitoring technical condition. It allowed the crew and technical specialists to identify faults in individual components faster without complete disassembly of the vehicle, reducing the time needed to restore combat readiness. As a result of numerous tests, the Chrysler project was declared the winner. It formed the basis of the future M1 Abrams. But winning the competition did not mean the work was over. On the contrary, the engineers faced numerous refinements, elimination of identified shortcomings, and preparation for series production. And it was then that it became clear that even the most promising tank cannot be considered outstanding until its technologies turn into weapons capable of changing the rules of modern warfare. When the first production Abrams began entering the troops, many specialists quickly realized that the main revolution was not hidden in the external appearance. At first glance, it was an ordinary main battle tank with a classic layout. But as soon as one looked deeper, it became obvious that American engineers had created a vehicle in which almost every major component differed from what had been considered the norm just a few years earlier. It was precisely the combination of these technologies that turned the Abrams into one of the most recognizable tanks of its time. The main weapon of modern modifications is the smoothbore M256 cannon of 120mm caliber. It was based on the German RH-120, but adapted to American production and operational standards. The barrel length was 44 calibers, a figure that ensured high muzzle velocity for armor-piercing fin-stabilized, discarding sabot rounds and excellent accuracy at long ranges. The crew could use several types of ammunition: armor-piercing, fin-stabilized, discarding sabot, with a separating sabot for engaging heavy armor; multi-purpose shaped charge rounds for destroying fortifications and lightly armored targets, as well as modern programmable munitions capable of effectively dealing with various types of threats. Thanks to manual loading, the commander could almost instantly order a change in ammunition type if the situation on the battlefield changed dramatically. However, powerful armament is useless without the ability to accurately hit the target. That is why enormous attention was paid to the fire control system. The gunner received a multi-channel sight with a thermal imaging channel, which allowed detecting enemy vehicles at night, in smoke, and in adverse weather. The laser rangefinder determined the distance to the target with high accuracy in a fraction of a second, after which the digital ballistic computer automatically calculated corrections. It took into account not only the range, but also the vehicle's speed, the gun's elevation angle, ambient temperature, atmospheric pressure, crosswind, and even barrel droop after heating. As a result, the crew only had to keep the crosshairs on the target, while the electronics performed a huge portion of the calculations independently. The weapon stabilization system was no less important. The two-plane stabilizer kept the gun nearly motionless, even when the multi-ton vehicle was moving over rough terrain. For the enemy, this meant an unpleasant surprise. The Abrams could deliver aimed fire without coming to a complete stop, significantly reducing the time between target detection and the first hit. This feature repeatedly gave crews precious seconds of advantage. The commander's station played a special role. The commander was not dependent on the gunner's actions and could independently search for new targets using his own observation devices with all-around view. While the gunner was tracking an already detected target, the commander was looking for the next one. This principle received the unofficial name Hunter-Killer. After one target was destroyed, the system almost instantly transferred control to the next, allowing the crew's tempo to increase sharply in intense combat conditions. Developers also did not forget about auxiliary armament. A heavy machine gun, the Browning M2 of 12.7mm caliber, was mounted on the turret for engaging light vehicles, low-flying targets, and infantry. It was supplemented by two M240 machine guns of 7.62mm caliber, one coaxially mounted with the main gun, the other installed near the loader's hatch. This combination allowed the crew to effectively engage a wide range of targets without expending the main ammunition load. An important feature was also the layout of internal systems. All workstations were designed with long-term operation in mind. Controls were arranged so that the crew could perform most operations without changing body position. Observation instruments provided a wide field of view, while the main control panels were placed within natural reach. For many hours of work in a closed fighting compartment, such details were of enormous importance and directly affected crew efficiency. The architecture of the electronic systems was no less thoughtfully designed. Already in the early stages of modernization, the Abrams received digital data buses that allowed various units to exchange information almost in real time. This simplified the subsequent introduction of new thermal imagers, communications equipment, navigation systems, and computing modules, without a complete redesign of the tank's construction. It was precisely thanks to this modernization margin that the vehicle was able to remain relevant for decades, gradually receiving ever more advanced technologies. But no matter how impressive this engineering work looked, the final assessment could only be given by real combat operations. One thing is to show outstanding results at a test range, and quite another to face an enemy where every decision is tested not by calculations, but by practice. It was there that the Abrams either had to confirm its reputation or turn into another expensive experiment that had not lived up to expectations. The moment of truth for the Abrams came in the early 1990s. Before that, the tank had covered thousands of kilometers in tests, countless firing drills, and exercises. But the real test always begins only when return fire is directed at the vehicle. It was Operation Desert Storm that was supposed to show whether American engineers had indeed created a new benchmark for the main battle tank, or whether their achievements were impressive only on proving grounds. Before the operation began, hundreds of Abrams of the latest modifications at that time were deployed to the region. They had to operate in unfamiliar conditions: vast open spaces, high temperatures, constant dust, and the need to fight at significantly longer ranges than anticipated in densely populated Europe. It was here that many technical solutions unexpectedly revealed their advantages. One of the main trump cards was the ability to detect the enemy significantly earlier than the enemy noticed the American vehicles. Modern thermal imaging sites made it possible to confidently distinguish armored vehicles not only at night, but also during dust haze, when conventional optics sharply lost effectiveness. Crews often had the opportunity to open fire from several kilometers away before their own tank came into the enemy's field of view. In desert conditions, this advantage became decisive. Equally important were the new armor-piercing, fin-stabilized discarding sabot rounds. To engage the most heavily protected targets, M829 series projectiles with depleted uranium penetrators were widely used. Thanks to the high density of the material and enormous kinetic energy, such munitions retained their penetrating power even at considerable ranges. Upon impact with armor, they did not use explosive. Damage was achieved solely through colossal speed and energy concentration over a small contact area. This is why even well-protected enemy tanks were often knocked out with the first hit. Great importance was also attached to first-round hit probability. In many previous conflicts, tanks were forced to conduct ranging shots, adjusting fire after initial misses. The Abrams, thanks to its sophisticated fire control system, often hit the target immediately. This sharply reduced the duration of fire contact and decreased the likelihood of return hits. In modern tank combat, Such an advantage is often more important than rate of fire or even armor thickness.
An additional factor was the high reliability of the running gear under harsh conditions. Wide tracks reduced ground pressure, allowing the multi-ton vehicle to move confidently over loose sand without a significant loss of speed. The torsion bar suspension effectively damped hull oscillations, maintaining platform stability for firing even when moving over uneven terrain. This allowed crews to change positions more quickly after opening fire, without lingering under possible return engagement. During the offensive, American units actively used their own tactical features. The Abrams rarely operated in isolation. It was accompanied by infantry fighting vehicles, reconnaissance units, engineer equipment, artillery, and aviation. Target information came from multiple sources simultaneously, and advanced radio communications allowed commanders to coordinate the actions of various units promptly. As a result, the tank became part of a unified combat system, where each vehicle reinforced the capabilities of the others. It was during this campaign that the so-called Battle of 73 Easting gained wide fame. Despite difficult weather conditions and limited visibility, American armored units managed to quickly detect the enemy, impose a favorable engagement range, and effectively exploit the advantages of their sighting systems. This episode became one of the most famous examples of modern main battle tank employment in the late 20th century, and significantly strengthened the Abrams' reputation worldwide. But along with resounding successes, less noticeable features also began to emerge. After long marches, support units noted the very high fuel consumption of the gas turbine engine. The enormous volumes of air passing through the turbine required constant monitoring of air filter condition, especially in desert conditions.
Even a slight decrease in the cleaning system's efficiency could lead to a drop in engine power and increased strain on maintenance personnel. In addition, the complex electronics required skilled specialists and a developed repair infrastructure, without which maintaining a high level of combat readiness became much more difficult. It was then that it became obvious that the legendary reputation of the Abrams was built not only on a powerful gun or modern armor. Behind the impressive victories lay a huge support system. Thousands of specialists, constant fuel supplies, spare parts, and complex technical maintenance. As long as this system worked without failures, the tank indeed demonstrated outstanding capabilities. But the next stage of its history would show that technological superiority always comes at a very high price. After the first resounding victories, it seemed that the Abrams had practically no weaknesses. However, the longer the tank remained in service, the more clearly the downside of its technological superiority became apparent. The gas turbine engine provided excellent dynamics, but at the same time turned the vehicle into one of the most fuel-thirsty main battle tanks of its generation. During long marches, fuel consumption could be several times higher than that of diesel counterparts, which meant a constant dependence on supply convoys. Any delay in fuel delivery quickly reduced the combat capabilities of the unit. No less attention was required for the air filters. The turbine passed enormous volumes of air through itself, so in sandy or dusty conditions, they had to be regularly cleaned or replaced. Even minor contamination affected engine power. At the same time, American engineers did not stop improving the vehicle. The M1 A2 modification appeared, featuring an independent thermal imaging site for the commander with all-round view, a digital data exchange system between vehicles, and more advanced navigation means. Later SEP versions received a new electronic architecture, improved computing modules, updated crew displays, and more advanced thermal imagers. Protection was also enhanced. Depleted uranium elements were incorporated into the design of certain modifications, and for urban combat, the Tusk kit was developed, including side-reactive armor, anti-shaped charge screens, a remote-controlled weapon station, and additional protection for the loader's position. All this increased the vehicle's weight, which on the latest versions approached 75 tons. Such weight complicated rail transport, crossing some bridges, and operation on soft soils, but allowed for a significant increase in the level of protection.
A new chapter in the Abrams history began in the conflicts of the 21st century. In Iraq, the enemy increasingly became not tanks, but anti-tank grenade launchers, powerful improvised explosive devices, and guided missiles. It was then that it became clear that even the strongest frontal armor does not solve all problems. Much more dangerous were strikes to the sides, rear, and turret roof, where the level of protection is objectively lower. Detonations from powerful homemade explosive devices damaged running gear components, road wheels, tracks, and torsion bars, and sometimes required complete evacuation of the vehicle. Urban combat showed that modern tanks increasingly face threats for which they were not originally designed. Events of recent years have only confirmed this trend. Modern anti-tank guided missile systems, attack drones, and loitering munitions have made the battlefield significantly more dangerous for any armored vehicle.
The Abrams remains an extremely difficult target, but absolute invulnerability never existed. With proper defensive organization, a favorable attack direction, or a strike against less protected projections, almost any tank can be knocked out. That is why debates around the Abrams still do not subside. For some, it is the best main battle tank of its generation, managing to outpace many competitors for decades thanks to the combination of powerful armament, high accuracy, advanced electronics, and thoughtful crew protection. For others, it is an extremely expensive and complex vehicle whose capabilities are fully revealed only with a developed logistics network, superiority in reconnaissance, aviation, and technical support. The truth, as usual, lies somewhere between these extremes. The Abrams indeed became one of the most influential vehicles in the history of world tank building. It changed the perception of what a modern main battle tank should be, set new standards for fire control systems, crew protection, and electronics integration. But its main feature lies not in mythical invulnerability. The Abrams became a legend because it managed to combine many advanced technologies of its time into a single combat system.